Monty are on, so I'll go ahead and start then. All right, so this session is about measurement and attestation. The previous session talked a whole lot about attestation and what you might measure in those attestations, so we'll get started here. Maybe. All right, so there are three of us presenting in this hour. I'll give you an overview of what this is all about. If you want the details, there are tons of details in the attestation spec. You can use it to put yourself to sleep at night, you know. Brett is going to talk about essentially what the protocol is, the attestation protocol could be in one environment in DMTF. And Monty will talk about how we are, how we would send allowed lists within the system. So let's go ahead here. I'll just go ahead. All right. So most recently, as in last week, 3 documents were produced or submitted to the OCP Incubation Committee for approval. The 3 of those are one that Yigal was the editor on, Common Security Threats, really, really good document. One on Secure Boot from Brian Kelly and Microsoft, and another really good one with lots of details. And this one that we'll talk about today is the attestation spec. All right, so why in the world did we need this attestation spec? So until now, servers, or we also know them as platforms, they had no standardized and open and automated mechanism to establish trust in the devices within them. The convention before this was that you used trusted suppliers. Your contract terms would say, thou shalt do this and supply this. But there was nothing in an automated way that systems could determine this trust. Oops, sorry, okay. So on the attestation side, this is the general idea of things, which is a device that wants entry into some platform of some kind. It must provide this attestation evidence. It reports its measurements, meaning in this case, here's an example. My measurements are, this is what I am. This is who produced this device. This is the firmware I'm running. And it's in a request that says, please, may I join the system? Now, the platform has to go and verify, okay, well, do I like you or not? And it can answer multiple different answers. One is, yeah, I expected you. I know who made you. I know that you're running the right firmware. You're great. Come on in. And so this is a successful verification. It might not answer that. It might say, yeah, I know all about you and I did expect you. I like you in general, but you're old, you're outdated. Your firmware is old, and go fix yourself and try again when you've been fixed. It might be that it doesn't fix itself, but some other system, even the platform root of trust itself, might be the one that's fixing it. But either way, it doesn't come into the system. It may go into a remediation network or some other place, but it doesn't come fully in. And then another option is, I have no idea who you are. Just go away. don't like anything you told me about yourself, just go away. So the device is not admitted. So that's the general idea of things that we're trying to accomplish. Here is a picture of, again, a very generalized version of the attestation protocol. it's way more detailed than this. It goes on for many pages of different pieces of this protocol. But to give you the general idea here is that the first thing you have to start off with is, what is it that the verifier is going to expect to receive? Because, you know, the device could tell it anything and it won't know if it's right or not. So this reference manifest includes, may include multiple things. It could be, what is the firmware that you're running? What are the keys that you used to boot yourself with? All kinds of different things, that your state, your configuration, what are your known good measurements, even metadata. So all that goes to the platform verifier here in this path here. And then the device goes into production, and its root of trust will measure itself. It measures the security state of this device, meaning, you know, what are the keys, what's the hashes of the firmware, and so forth. It then sends these to the verifier. Now, notice here, this isn't just a one-way, here are my measurements and I've signed them and I'm done, because you do need to have a challenge response protocol so that the device can't replay a good answer that it had yesterday. It has to be fresh, and therefore you need a challenge and response protocol. So this is, and Brett will talk about this protocol here. The verifier then has to verify the attesters. What's the identity of this device? Is it what it's supposed to be running? This is the verification against the manifest, and then decide what to do with it. So that's the simplified view. Sorry, my system is not cooperating here. All right, so next we're going to hear from Brett Henning from Broadcom. Brett's going to talk about this part here of the protocol itself. So if I can scroll to Brett's slides, SPDM spec. All right, Brett.
Well, thanks, Elaine. As an introduction, I'm involved in both the OCP security project as well as the DMTF Security Task Force, which is the group that produces SPDM. So I will be bringing in pieces from each and really trying to show how the SPDM protocol enables the capabilities that are described in the OCP attestation spec. As I go back and forth between those roles, I'm going to try to keep it clear where I'm pulling source material from. And just another note, I know that in an earlier session, there was discussion of DMTF and some potential futures for SPDM. The portions of SPDM that I'm going to be speaking about in this session are all publicly released. So this is all stuff that you can do today. Go ahead and go to the next slide. So this slide is showing the challenge portion of the protocol. And this is what Elaine was speaking about as that step that needs to happen between the platform verifier and the attester device. So it's not enough to just have an attester device say, here, I tell you this is who I am and you have to believe me. We need something that's more secure than that, and something that is resilient to things like replay attacks. So that's where this challenge protocol comes in. When you go through it in SPDM, the first thing that happens is you go through a set of commands where you're going to agree on spec versions, capabilities, algorithms, kind of the normal negotiation that sets up a lot of different protocols. And through these steps, you can you'll figure out what the responder is capable of and whether or not you at least accept the level of security that the attester device has. Next, you would read the device's certificate chain. And so the device can return a certificate chain that's been provisioned to it. And then there are a bunch of verification steps that can be run on the certificate chain itself. And now comes the challenge piece. And this is what Elaine was alluding to, is there's a challenge where the platform verifier has to go to the attester device and challenge the device to make sure that it really is the one that should be sending back those certificates and not just spoofing the operation. And the way we do this is through a couple of steps, but it involves using a challenge request with a nonce. And then the attester device will build a response that contains its own nonce. So both ends are contributing large random numbers to make sure that the request and response pair are fresh and unique. And then the responder, the attester device, will sign the response using the device private key. And this private key will correspond to the public key that was returned in the certificate. And then when this is sent back, that is something that the platform verifier can go through and check and make sure that the signature is correct. So at this point, we get to this state that we get some of the characteristics that Elaine was speaking of. So we know what the device is, right? We know who you are. We know who your manufacturer is. But we're not all the way there because we don't yet know the state of the device. But we at least we're starting to get a picture of what the device is. So go ahead and go to the next one. So the way we deal with the state of the device is through measurements. And for those that aren't familiar, measurement is really just a term for a hash or some other representation of a digital entity. It could be firmware, it could be state. So once the attester device has been challenged and the platform verifier is happy with the challenge response, then the platform verifier can move on and go through a set of measurements. And it does this by issuing a get measurements request. The get measurements request itself can also include a nonce, and oftentimes would. When the attester device receives this, it'll build a list of the measurements and it will sign it if it's requested to do so. And again, that would be signing with the device private key. And that again will ensure that these measurements are coming from the attester device and not coming from some kind of attack or just trying to replay measurements that it saw at some point in time and thinks are good. So take all that and send it back to the platform verifier. So at this point, the platform verifier can say, now I know your state and I know if your firmware version is valid. But in order to actually know what those firmware versions and measurements are supposed to be, it needs a source of that information. And that's something that Monty is going to be talking about in a few minutes with the reference integrity manifest. He's going to be talking about a way to actually let the platform verifier know what answer it should be getting back from the attester device. Go ahead and go to the next one. Now, another question that, actually there's a question. So how does the verifier of the attester of the attestation know that the public key of the device is original? Does each device have a unique key per device or same for a series of devices? So the public key would be unique per device. And it'll be contained in a certificate that's also unique per device, but that certificate will be part of a chain of certificates. And so the platform verifier can walk up that chain of certificates and make sure that it attaches to a root certificate that the platform verifier knows about. And that way you would know it was signed by or endorsed by the owner of the known root. And then you would also have information about the uniqueness of that device. So, okay, so when to perform attestation. This is a topic we've gone through, boy, several times on the OCP security calls. It's been quite a conversation. At a high level, there are really two, and I'll say really three options. So the first option is just reset the system as normal. And in this option, you would let the system come out of reset and hold the entire platform in some kind of fenced off state until attestation completes. So in some environments, that might be holding the system in post so that it can't go to the OS, or however else the platform owner decides they can keep the system safe. And then you would have a platform verifier run around and go to each of the attester devices and make sure that each one of them passes. And then, as Elaine mentioned, if they don't pass, then the platform applies some kind of policy to them. And that might be, we just shut down the platform and send up a flag saying, come service the platform. It might be turning off individual devices. That's up to the platform owner. A second one, and this is the one that we spent quite a bit of time talking about in the OCP calls, is an option of holding all the devices in PCIe reset while you perform attestation. And obviously that attestation would be over some kind of sideband bus or out-of-band bus. Typically that would be I2C today, though we've had conversations about potential future directions that are faster. But this one requires a pretty high level of device support. So the device has to support letting its CPU come up to a highly operational state while the PCIe bus is held in reset. We did include a section on this, including a rough timing diagram in the OCP attestation spec. So definitely for people that are interested in or have questions about option 2, I would encourage you to go look at that section of the spec. And then a third option that you'll also find mentioned in the spec is, in some situations, the platform vendor uses a root of trust device that's attached to the attester device. And so they might actually have just a root of trust that sits on the SPI bus and responds to attestation commands. And that becomes the security gatekeeper for the device. And that would fit well into a sequence a lot like number 1, but it does require some staging of the resets because you have to bring in the platform up in a specific order. The big takeaway in here, though, is ultimately it's up to the platform to decide which approach to take. As long as devices are capable, then it really comes down to a platform decision and what the platform can tolerate versus what it can keep secure. Go ahead and go to the next one. Now in this slide, we're shifting a little bit. In this slide, this is coming directly from the OCP attestation spec. So one of the sections in the specs speaks directly to required capabilities. And this is specifically saying these are required capabilities for an OCP attestation compliant device that uses SPDM. And the reason OCP calls these out as required is because these are optional in the SPDM standard. But OCP said, in order to comply with these flows that we had a few slides back, here are things that you have to do. And the list is pretty short, but this is based on specific SPDM capabilities. It does require at least version 1.0, but recommends the latest version. It requires the ability to support certificates, a challenge, and measurements, with the recommendation that an attester device should support signed measurements. And then for algorithms, there are a couple of algorithm sets in here that are recommended. There's a minimum set of required algorithms, and these are largely based on the OCP secure boot spec. So it's aligning algorithmic strength with the secure boot spec. And then down below that, you'll see there's a list of recommended algorithms that really go to a much higher strength. And that for that one, it's looking towards future proofing. Go ahead and go to the next slide. So this slide gets to the next step that SPDM supports. So everything we've been covering so far is about proof of identity, proof of state, proof of current firmware. This is what SPDM can do going past that. So after you complete measurements and you're happy with the state of the device and you've decided you're going to admit it to the system, then you can go through a key exchange. And as part of this key exchange protocol, you can do what's called mutual authentication. So the attester device can actually turn around and ask for the identity of the platform verifier. The reason it would do that is because we're setting up an encrypted channel, and the attester device might have a policy that says it needs to know who it's setting up this encrypted channel with. But once this is done, then you get authenticated encryption. So you can use authenticated encryption not only for security protocols, but for other things. You can use it to protect a firmware push to the device, management capabilities, and all sorts of things. Go ahead and go to the next slide. So on this slide, this gets into how these different pieces fit together. And I know we talked through this a little bit in the morning session, but I want to spend a little bit more time digging into how SPDM enables these different management command types. Starting at the bottom, you see that SPDM is designed to run on top of MCTP. So it takes advantage of any bus that has an MCTP binding. You can just take SPDM and just layer it right on top of that SPDM binding and start going. That also leaves open a couple of other possibilities. So at the bottom, other buses that aren't listed here, it's possible to create MCTP bindings for those buses. That's a fairly straightforward process. And so a platform vendor could create MCTP bindings for them. And then there are also a number of organizations that are partnering with DMTF. As we mentioned in the earlier talk, there are a number of organizations that are partnering with DMTF to create bindings for their own buses. And so the idea of SPDM is SPDM itself was designed to be very agnostic to the underlying protocol. It accomplishes this through creating a message type that specifically binds it to MCTP. So even if you have some kind of different or exotic bus, that can be bound, you can create a binding for the SPDM spec to that. What we're showing on the left is what are called type 5 messages. So these are messages that do the challenge and authentication protocol. These do the measurements command set. Type 5 is really the establishment phase. And then once you're done with type 5, it can move to type 6, which enables secured messages. And these are messages that are either authenticated with a MAC or they're encrypted and authenticated. And once you get into these secure messages, or type 6 messages as they're called, they can carry any other type of MCTP message. Or for that matter, you can come up with bindings to other specifications and carry those as well. But examples of what can be carried are PLDM, vendor-defined messages, RDE, really the entire suite of management messages could be carried over this. Let's see, go ahead and go to the next slide. So this is just a list of relevant references for SPDM documents. So the first one on here is the standards portal. This is just where publicly released standards are available. The second line is the feedback portal. DMTF welcomes feedback on any of the DMTF standards. So anyone who has feedback, go ahead and send it through the feedback portal, and it does make it back to the task force. And then below that is a list of normative documents. So these are our standards documents. A couple of these are listed as work in progress. Those documents will be replaced with released versions, hopefully in the near future. And then the security task force also put out one informative document. This is a white paper. And the white paper just goes through use cases and recommendations and some discussion on why things work the way they do. So it's information that's considered useful to implementers, but really didn't fit into the context of a spec. So that's it for the slides I had. I know I've seen a couple questions in here. One question is attestation of hot swappable devices within scope. It is, at least in my view, it's within scope. There has to be a mechanism for the platform verifier to determine that a hot swappable device has shown up. But I think it's absolutely within the realm of reason for a verifier to come in and say, no, you're not allowed into the system without being checked out, even if you were hot added. Another question was, assuming a device is not able to attest successfully, how is it going to be kept from accessing memory? And that would be, some of that falls to platform design. There's a belief that, that the view is that the platform has to be able to keep out devices if that's how they want to do it. This is one of the reasons that we mentioned that second option, though, of holding devices in PCIe reset until they successfully attest. That these types of concerns are exactly the reason that flow exists. So if as a platform designer, that's how you want to attest things, you can make sure everyone passes before you let them have access to anything on the main data bus. And then another question was, has SPDM for attestation and also encrypted communication been approved by OCP? So the current OCP attestation spec specifically references attestation. It was built around the SPDM 1.0 spec, which was very attestation centric. And so it, yeah, so that's kind of where it stayed.
Yeah, at the moment, it's been submitted for approval by the OCP Incubation Committee, which is like a technical steering committee, and we're waiting on that approval.
Thank you.
Yep.
Yeah, and I definitely think the group will talk about encrypted communication as a future movement, but right now it was very, as a first step, it was very focused on attestation. Let's see.
We're gonna have to move
on. Yeah.
on. So, and then more questions at the end.
Okay, and yeah, so go ahead, Elaine. Thank you.
So thank you very much, Brett. Very informative. Okay, so we're going to move on to Monty Weissman from GE. He's also well, I'll let him describe what he does in TCG, but we are now moving on to this part of the big picture of the protocol, which is, what does this reference manifest look like? How do you get it? Where does it come from? And then once it's here, how do you use it? So I'll move on for Monty.
Yeah, thank you. I assume you can hear me?
Yes, we can hear you. We can't see Monty because of his,
yeah, I've had, of course, the way things work is my ISP modems died this week. So I'm waiting for a new one. So I'm tethering on my cell phone. It's already dropped a couple times today, so I'll dial in if I have to. Hopefully, I won't need to. So that's the disclaimer. But yeah, I'm not going to push it with the camera. There's no way. Anyway, okay. So we're going to start with, and this was stated in an earlier presentation today, where if you don't trust the hardware, none of this makes any sense. So the problem statement we are starting with is, how do you trust the hardware? Well, today we've basically got kind of this physical manifest and delivery mechanism, and we hope the box we get on the right side is in fact the box that was made on the left side. So this is just kind of introduction to the problem statement. Just go on to the next slide, please. So we've talked a lot about attestation. How do you get there? Well, if you decompose attestation, this is kind of a background. It all starts with a root of trust of measurement, something that you trust, something that's in the hardware that you trust the manufacturer has done correctly. So you have to start with that point. But then you've got all these what's called mutable components. Platform firmware, the boot firmware on a PC client, for example, or servers, or actually any system. Typically, it's not in ROM. They want to be able to update it in the field or otherwise. You've got option ROMs that boot, and again, this is very PC centric, but it actually does apply to other platforms. It then goes to a boot manager, Grub, for example, on Linux-based systems. Then you've got an OS loader, an OS, and so all of this, and there's millions of lines of code here that run until you finally get to the operating system. And most of the code to the far left of the operating system, once it's executed, is completely invisible. And so what we've done, and so yes, I guess I didn't finish introducing myself. Along with working for General Electric at the Research Center, I co-chair several of the working groups, and the one that's of interest here is the infrastructure working group, which is defining the structures to do the things I'm going to be talking about here. So along this boot path here, you're creating a sequence of measurements, and in a very TPM TCG centric description here, we are going to place those measurements into a register called the Platform Configuration Register, or PCR. And at the same time, we're going to create events outside structures, outside the TPM, because the TPM has very limited resources, that describe each one of these events that, of course, as I described, are hidden once the operating system runs. So what we're going to do is we're going to build up a sequence of these events, and again, the details of which and how you accomplish them and verify them in a way are a bit outside the scope of a short 20-minute presentation. But what we're going to get to is at the end is some verifier is going to want to look at all of this evidence, whether it's the value, the PCR, as Brett described. He described the protocol. You know, the verifier, as we're describing it, is going to look at all this evidence that that Brett has described as we've managed to secure. But how is he going to verify this? What does he use to verify the information? So again, go to the next slide then. So these are kind of the problem statements. So what we're going to start with, and so I'll advertise what's called the platform certificate a little bit from TCG, is we will use what's called a platform certificate provided by the platform supplier that attests to the hardware properties of the platform itself. So now we've got some mechanism, and I can send you a link if you'd like. We've done several RSA presentations describing this, and again, the details of which are out of scope for this discussion. But the main thing that we need to get across here is that the root of trust of measurement, which is a piece of hardware, is attested to during this operation. So making the assumption that we've done our job right, and the attestation of the static components or the platform itself, you can trust on the right-hand side. We can therefore trust the information from the previous slide is what are the measurements? What actually is the content of the firmware of the operating system, the bootloader? What actually booted this machine? So at the conclusion of this, assuming you follow the platform certificate protocol, you have a way of believing not just the hardware, but the information that comes to it. So as was mentioned, the missing ingredient here then is, and go on to the next slide here, I guess, would be the missing ingredient here then is we need some sort of RIM, reference integrity measurement, some manifest, if you will, or golden measurements. It's called a lot of different things. We in TCG are calling them RIMs. That from the manufacturer might be the same supplier as the hardware, or it might be someone else. It might be a VAR, for example, who's taken this platform and added their own firmware to it in some authorized way, and then resell it. In the simplest case, though, it would be the original manufacturer of the platform. But then, of course, you've got other components like the bootloader that would most likely not be put on by the manufacturer. So what you need then is from some authority that you trust, a set of reference measurements to feed into the verifier on the other side, which I didn't depict, but that's clearly on the other side of this equation, to say, okay, well, I trust the hardware and I have these measurements, what should they really be? And so this is one of the things we're working on. In fact, one of the specs was just published the other day. So there's actually an update to one of my links, one of my links in the slides. So that's what we're that's the work that we're describing here, is a standardization of this reference integrity measurement. So if you go on to the next slide then. All right. So what we've done is we've adopted the overall structure of the SWID tag, and the SWID tag is actually an ISO standard. It's actually like all ISO standards. It's behind a paywall. So the NSA and NIST has been kind enough to the industry to basically take that specification and kind of sort of rewrite it in NIST IR 8060. So you actually don't need the to get the ISO spec NIST IR. I've been told to about a 95% accurate completeness rate is essentially as described in the ISO spec. We decided on SWID tag because that's commonly used to describe software. The software that's running on the system was originally, I think, developed mostly for licensing, but it is more and more being developed as a mechanism to attest to the integrity of the file system. But okay, so we could, and the idea behind this was we really wanted one tool that the verifier can use to do things like verify the firmware, verify the boot manager, and also verify OS and potentially even things like IMA measurements, integrity measurement architecture, that would measure actually the files and provide measurements of the files and attest to the files that are running at runtime. So that was TCG's logic in starting with SWID tags, because we felt that was already a standard that was adopted across Linux. Actually, Microsoft has adopted it. So we felt like we didn't want to reinvent the wheel with a new set of standards. But one of the problems with the SWID tag is it's very file-centric, file system-centric. And I'll go into how we solve that in a later slide, but just wanted to kind of justify why we started with SWID tags to begin with. Does that make sense? And if anybody's got any questions, please ask along the way. Okay, so is there a question?
Keep going.
Okay, yeah. So wrapping this all together into the next in the final slide, what we're attempting to accomplish here is, if you combine the attestation of the hardware using platform attribute certificates, as well as the RIMs coming from, again, either the same source or a different source, there's no requirement for them to be the same, that at the receiving end, you would be able to assert the identity of the platform, regardless of whether it's been a truck and in a warehouse. And in some cases, industrial controllers actually might sit in a warehouse, for example, for a number of years, used as spares or whatever. You'd like to be able to know when you bring these back out that they are in fact the same ones you put in there or came from the same source. So that's the hardware component. And as depicted in this middle, now we've completed the picture of provided the verifier on the on one side with the reference measurement signed by, again, nominally the supplier, but if it was modified by a VAR, by the appropriate trusted agency. And on the right-hand side, then, as very similar described by Brett in the previous discussion, in TCG, we use a protocol called a TPM quote. That's the actual TPM operation. We are actually defining a protocol for conveying this using the nonces, very similar, and nonces and time-based. There's actually a time-based mechanism to assure freshness of the quote. But from a RIM perspective, that protocol doesn't matter. We're simply going to provide the information to the verifier to say, okay, this is what came from the device on the right-hand side, and this is what should be there. And the verifier will then be able to make a decision as to whether that platform is in a proper state. The next slide which we will spend most of our time on here, will actually describe what we've done actually at a very high level. Don't have a lot of details here. The specification would provide that level of detail. So as I said earlier, we started with SWID tag schema, and we didn't want to do a lot of modifications to it. So there's a couple optional fields that we used, and we took those fields and added some smaller extensions to them, because as I said before, one of the problems we had, especially with the firmware and the bootloader, is the measurements and the integrity, the reference measurements don't map very well to file systems or to files themselves. So what we did is we created what's called this base RIM and used a few optional fields that we were allowed to use. We didn't want to have to go back to ISO and ask for a whole new revision of the spec. So we identified a few fields that we could use to put small pieces of information, like if you just had the PCR information, which is the aggregate of all of these entries, and that's all you had, then there's enough room in a single SWID tag to put that information in there. And so this would be what's called a direct payload type. If you had just a small piece of information, this might be applicable to small devices. Maybe we'll use it for something like a DICE type information. We haven't gone there yet, but instead of a TPM-based implementation. But this all, again, fits within the SWID tag schema. The one requirement we do have, which the ISO spec does not have a requirement of, but they do have a schema for a signature. So obviously it doesn't make any sense to provide a reference measurement without somebody actually digitally signing the information so that you can then trust it. So we do actually require that optional feature be deployed. On the right-hand side, you have a more complex RIM, say, for example, on a PC client. When I talked about the measurement process earlier, I mentioned there's multi-stages, multi-measurements, millions of lines of code, in UEFI in particular. You've got, the SE code, you've got the SEC code, you've got the Dixie code, and you've got option ROMs and UEFI drivers. And all of these would get measured into the PCRs, but if you just relied on the PCRs, which is simply a hash aggregate of all of the information, you don't have any resolution. If something's amiss and something doesn't match up, if that's all you're relying on, you have no way to decompose it. In fact, if you could decompose it, you've broken the hashing algorithm. So what the PC client has done is, along the way, as you're taking these measurements, you're producing what's called event log entries, which is dedicated C structures nominally that describe each individual measurement that happened along the way. Well, we started looking at, the SWID tag, and as I said earlier, we didn't want to do a massive surgery on the SWID tag itself. And we also recognized that the PC client isn't the only platform on the planet. You have lots of different classes of platform. And you might have different ways of representing these different events that occurred during the boot process. So we wanted the base RIM, the actual SWID tag schema, to remain static across all of these different platform classes. So what we did is we simply defined, again, using some extensions that were already available to us, we simply created basically defined a type and a hash field. And that hash field would contain, each one of these would contain a hash of what's called a support RIM. So the support RIM, though, is not based on SWID tags. It's based on the platform-specific way they're performing the measurements. And so you have what might be shown here is kind of a third dimension of you might have. In fact, we just published the specification for a PC client, which actually describes how in a PC client these support RIMs are structured. We would expect if there was another class of specification, servers would probably be the same as PC client, since they use the same structures, but maybe industrial controllers will be different. We don't think so, but they might be different, or other classes of machines might be very different. So they would have their own support RIM definition, but the main RIM specification, the base, what's described here as the base RIM, would not change, and that would remain a SWID tag type structure. So that's essentially, and then we could go even deeper. We've thought through, which I don't have a slide for because it would take us well beyond the time limit. But we've gone through scenarios where you've got these what's called RIM bundles, which is sets of these. Well, what about a firmware update, right? If you update the firmware, now you have to have a whole new set of these, right? To say, here's the information for the new one. So we've actually, if you go look at the specification, the information model in particular, you'll see the way we've done the complete life cycle of these RIM bundles, even including things like VARs. What if a VAR added some firmware, added some code, but then the original manufacturer had a BIOS update, which affected what the VAR did. So there's lots of permutations that we've taken under consideration, and again, that justifies why we really based everything off this RIM bundle, and again, based everything off of the SWID tag. So that was an awful lot, probably about an hour and a half's worth of discussion in about 10 minutes. Kind of go before I go on, which is really some summary slides. Are there any questions about how that works and why we used SWID tags as a basis?
Well, we're running low on time, so why don't you wrap up?
Okay, sure. I'll just wrap up then.
Questions?
Yeah, so this is just kind of the summary slide. We believe using the TPM is the best way to provide this sort of attestation. I will add verbally DICE is becoming predominant, especially on smaller platforms. Using the endorsement key and the platform certificate is the way of asserting, determining the authenticity and the integrity of the hardware, and using these using the SWID tags as a way of determining the authenticity of the firmware. And we can probably just skip. I think there's a let's just, for the purposes of time, I do want to go to the download and review. There's a number of open source, mostly I want to point to the HERS project. Google has a Go attestation project, which is essentially HERS functionality done in Go. IBM has their own essential implementation. I just wanted to point out that this is real, and there are actually real live proof of concept implementations based on this. With that, people can read the references offline. I'll defer to questions now.
All right, so one question is, why do we need both the platform cert and the RIM?
Well, the platform cert attests to the hardware properties and the root of trust of measurement. And that's static. That doesn't change over time. So the RIMs only attest to the mutable components, the firmware. But the platform certificate is an attestation of the hardware, and for the purpose of the RIMs, more importantly, can you trust where does the root of trust of measurement come from? So we believe you need both.
All right, Another question is, does the verifier in the DC need to attest only the RIM, but not the device identity, since it can't on the RIM supplier that it verified the device identity?
Yeah, they certainly can. Again, we created no technical dependency between the two. So if you trust the physical supplier and you trust the delivery truck that brought it to you, and you have no reason to not trust the hardware, and you can look at the specs, yeah, there's no reason to use the platform certificate in that case. You can rely simply on the RIM.
Another one is, will the root certificate reside in the platform so that certificate verification will not require going outside of the platform?
So that's a really interesting question. We have actually proposed putting it in the EFI partition, which is common to both Windows and Linux. That has the advantage, as you say, of not having to go outside. That's especially important for OT environments. The downside of doing that is if you replace the disk or you decide to wipe the disk for some reason, now you've lost it. So we believe the answer is going to be both.
So both, and that you have to go outside initially, and that
the manufacturer, the manufacturer should provide a place to go get it in case you've lost it on the hard disk. So you should it should be in both places.
So I guess one more question that just showed up is, how does the verifier locate the correct RIM for a specific platform?
We have pointers, well, going back to the platform certificate, there are pointers in the platform certificate for where, for a URI, for where to put the RIMs. There's no requirement there, again, the supplier can place that where they want. It could be common knowledge. We thought that was a convenient place to put it. That does cryptographically, in a way, bind it to that location, but there's no requirement to do it that way.
Lonnie, I have one. Has anyone implemented RIMs for device firmware?
Since the spec barely came out, I don't think anything's in production. I do know of, I probably read that I have to say here, but I do know of manufacturers that will be producing them. It will be a requirement, we believe, in a upcoming government specification, or at least a strong recommendation.
Cool. I guess we're at the end of the session, right? So here are some other references if you want to join any of the projects that in OCP, particularly our security project, or you want to send comments on any of these standards. We got some links there. And I think that is it. We ran out of time.